Okay, so we are going to just do a course wrap up today. We are basically done with all of the main technical material. So this is just going to be taking a look back at everything we have done, and also, you know, giving you some final pieces of advice on the final exam. Okay, so final exam next Friday, 13th. Okay. It's comprehensive, which basically means everything we have done from the beginning through today is fair game for the test. The exam tends to emphasize the latter topics beyond midterm 2 because that's something you have not been tested on. But pretty much everything is covered for the final, the comprehensive final. Okay. So more emphasis on the latter lectures 16 onwards, but 1 through 16 are also part of the test. Okay, so in other words, you need to make sure that the new material, file systems, IO system, distributed system is something that you are familiar with because there will be more emphasis on that in the exam. Okay, please ask me questions as we go along. So this is just a recap, bird's eye view of the entire course until last until the last lecture. So we are done the four. We are now done with the four major pieces. Okay, the processes and threads part, the memory management, I/O systems, file systems, and then the networking and distributed system. Okay, so we looked at. This is the table that I put up in the very first, maybe the second lecture, okay, which basically said these are the hardware abstractions you find on your system. There's a processor, there's memory, I/O devices, there's a disk, there is a network card, and basically we said what we want is to understand what OS services are being provided in order to manage those hardware resources, and what do the users see, how do the users interact with the operating system, and that's basically what we have covered here. Basically, for manage the CPU, we have processes and threads, and the topics we covered are process management, scheduling, protection, accounting, and so on, synchronization. For memory management, we have address spaces that are used by processes and threads. We talked about protection of memory, memory management schemes, virtual memory, on-demand paging, and so on. For I/O devices and disks, okay, you basically see files and the hardware devices themselves. And we have talked about I/O management, writing device drivers at a very high level, file systems, file management, and so on. Okay, and the last piece is networking. And I talked a little bit about the network protocol stack, security aspects, protection, and distributed file systems. Okay, and also remote procedure. So that's basically the snapshot. And I'll talk a little bit about each of these topics just as a recap. Okay, you can ask questions if you uh, think that some of these things are not clear, for instance. So, highlights of process management. If you remember, way back when we talked about what is a process, it's basically an execution context of a program. We talked about context switches, switching between one process from one process to another. What happens during a context switch? Save the state of a process, run the CPU scheduler to pick the next process to run, load the state of the new process. Okay. We talked about what is a thread. Okay. Threads allow you to have multiple streams of execution within an address space. Okay. So same address space, memory. So the stack segment is distinct for each thread, but the heap and the code segment are shared. Each thread executes through the address space, and it looks like sort of an independent stream of execution. Okay, we talked about different types of threading, user level, kernel level, looked at examples of not examples, rather advantages and disadvantages of what user level threads give us, what kernel level threads give us, and so on. Okay. Then we talked about CPU scheduling. Yeah, I mentioned several different scheduling algorithms, starting from first come, first serve. We talked about round robin, shortest job first, okay, which is optimal in terms of waiting time, and multi-level feedback queue, which is basically what most operating systems, at least Unix-like operating systems, use today. Okay, in that context, we basically said processes could be I/O bound or CPU bound, and you would ideally like to have a scheduler that gives priority to I/O bound processes. Okay, because these spend a very little time on the CPU and to go back to doing I/O, so they are your short jobs. So you want to somehow favor the short jobs and let them go back to doing I/O, and then use the remaining time to run your CPU bound jobs on the CPU. And basically, we said multi-level feedback queues explicitly favor IO bound jobs by giving them higher priority. Okay, so that's basically where we left off the scheduling part. Okay, then we spent quite a bit of time on synchronization. Okay, we looked at logs, semaphores, and monitors. And the basic point you need to take away is not just how they are used, okay, which is certainly important, but also how they're implemented, okay, using test and set instructions or masking interrupts and so on. Okay. Now, Lab 2, which was returned to you just before the Thanksgiving break, focused on synchronization. Okay. And although now some of the synchronization material is covered in 230, okay, so 377 has been de-emphasizing materials on threads and so on. But nevertheless, I was somewhat surprised to find that the performance on Lab 2 was worse than Lab 1. And I thought it would be better because you already encountered the material once before, at least at some level, and you were seeing it for the second time. So I just wanted to pause and ask some questions about, is synchronization material still hard to understand, hard to program? It's useful feedback for me. We can't do anything about it now because Lab 2 is already gone by. But it's good feedback for us for subsequent iterations of 377. Any comments on general comments on thread synchronization, coding in threads and so on? So I don't understand why the performance was somewhat worse because, and I saw a little bit of that also in the exam. Questions that related to synchronizations, people had more difficulty than I would have anticipated. Yes.
For 230, we didn't really use Java libraries that much.
Did not or did?
Didn't.
Did
we
not.
mainly use like C.
Okay. But you used P threads there. What did you use for? Did you have threading exercises?
We had some.
So there was a lot of code given, which was I didn't
learn much because there was too much spoon feeding. Okay. See, last time I did not even have an exercise on threads because I said threads are all now part of 230. We will talk more about. So we actually had a memory management lab, but then I am finding that although we said threads are now covered in 230, the background that you need to do threading is still not there, which is why I reintroduced the lab. But I had hoped that given that you've seen some of it once, it would have been better. But it looks like we have to emphasize more of that. Because threading and concurrency and synchronization is very important. I mean, if you write any real piece of software, you'll see that most of the code is multi-threaded. If you don't understand how to do it well, you're going to have trouble writing code when you go out do a job and so on. So it's actually an important aspect. Okay. So are RPCs and RMIs, which I did not have that extra lab that I was talking about here, because we traditionally have not done that, but I had wanted to introduce that component as well to the course. How is lab 3? Okay, which has of course no threading whatsoever. Yes.
It's a little hard to understand how to implement them, but once we understand how to think about it, it's easy.
Okay. Any other comments?
I think it's easier than lab 2.
Okay. Well, if there's no synchronization, it should be easier. Can't have race conditions in your code. Everyone done with the lab, or you're using late days?
In progress.
Yeah, in progress.
I have a question on that.
Oh, sure.
How are we supposed to test and decorate?
How are you supposed to test? Well, you can test by when you create the file, see what blocks you wrote to, what blocks were allocated, and if you read the file again, make sure that the same blocks are being read, because we are not asking as much as what is being read and written. It's just that is your file system code able to go and get to the files at the same time. The other important thing to keep in mind is your file system needs to be persistent, which means you better test the case where you shut down your Java program. Okay? The disk file is on your disk. You restart it and attach it to the disk. All the files you wrote previously should still be there. Okay? Meaning, if you have actually kept some data structures in memory and forgotten in your code to write it out to disk, then your code is not correct, because this is a file system. Okay? If you have inodes that you're somehow forgetting to write back to the super block or whatever, and you shut down your Java process and then you restart it, that state will be gone. So we are going to make sure that whatever code you write actually is writing persistently to disk. This is what you expect in a real file system. If you shut down your OS and you reboot it, you don't expect the files to have disappeared. Okay, so just make sure you do the extra sanity check where whatever is on your disk file, even if you shut down your Java program and restart it and reattach it to your disk file, whatever was done previously is all intact, that nothing has disappeared. Okay, there's something important to keep in mind. I don't know if it was made explicit, but do make sure that that is the case. Okay. Okay, anyway, so let's continue this. So, synchronization, we spent quite a bit of time. Perhaps in future iterations, we'll emphasize this a little more in terms of labs and so on. Okay, but we talked about locks, semaphores, monitors. Okay, and then we spent some time talking about deadlocks, deadlock detection, deadlock recovery, and so on. Okay, so deadlocks are something that you need to make sure your code avoids. Okay, as I said, from an operating system standpoint, most OSs don't do anything about deadlocks really. So this material is mostly here to help you understand what they are, because when you write multi-threaded code, if you have bugs in it, you will see deadlocks. Okay? And the goal of the whole exercise was to have you understand what are deadlocks and how you can go about dealing with deadlock. Okay? In most cases, what you do is to write code in a way that deadlocks can never occur. And we talked about some simple rules by which at least one necessary condition becomes false, and then you can avoid deadlocks altogether. Another important takeaway, even though operating systems don't actually do much about deadlocks whatsoever. Okay. Next big topic was memory management, followed by I/O systems. So memory management, I mean, on some of this material, hopefully still fresh in your mind because it was on the exam and whatnot. So we talked about a variety of different memory management scheme, starting with contiguous allocation, which involves dynamic or static relocation. Okay, then we said that can lead to fragmentation. So we said the right way to allocate memory is chop up the RAM into fixed size chunks called frames, take the address space, partition it into fixed size chunks of memory called pages, and pages are assigned to frames. Okay? So we relax the assumption that the process is contiguously located in memory. Okay, bits of processes, i.e. pages, can be anywhere, and you keep extra information, which is tables, to tell you where the pages are in main memory. Okay, so you have a page table associated with the process. So to find a particular byte in the address space, you index into the page table, you find the right page and frame, and then you find the right offset within that frame. Okay? So this is basically something that all operating systems do to avoid fragmentation. Okay? It gets rid of external fragmentation altogether. Okay? We talked about implementation issues, which are very important, because if you keep the page tables in memory, every memory access becomes two memory accesses. Okay? One to access the page table and one to access the memory location that your process is accessing. That's going to slow you down tremendously. Okay? So as a result, we said you will use some extra caches, which is a translation look aside buffer. Okay, the TLB caches recently used page table entries. So page table is in RAM, it's actually in kernel address space. You take some of the page table entries that have been recently accessed, put them in the TLB, which is faster memory. So whenever you have a TLB hit, you do not pay the cost of two memory accesses. You pay the cost of a TLB access, which is fast, and the memory that the memory access that the process is trying to perform. Okay, so it is a important hardware addition to help implement paging efficiently. It's not required, but it is a performance optimization. So every piece of hardware will have a TLB, because otherwise the performance will be really bad. Okay. So then we looked at on-demand. Well, we looked at segmentation, which is the compiler's view of a process, and we said that the compiler views a process as a collection of segments. Segments are of arbitrary sizes. So if you just do pure segmentation, you will have fragmentation. So what you do is you take each segment and you page it. You chop it up into fixed size pages, just as we did with the pure paging scheme, and then you page each segment. Okay. So now you need a segment table to index into segments, and you need a page table for every segment. Additional data structure, more bookkeeping. Okay. And the final scheme was on-demand paging, where we relaxed the assumption that the process has to even fit in memory. Okay. You can have processes that are bigger than size of your RAM. The total number of processes and their memory requirements will far exceed the size of memory. Okay. So your OS is no longer restricting you to having processes that fit inside RAM. Yeah, the way you do this is you actually keep the processes on disk and you bring bits of processes into memory as and when needed. You page them in. Okay. So essentially, whenever the process touches a page, the page is not in RAM, you have a page fault. You basically execute the page fault routine in the kernel, okay? Bring that page in, resume execution of the process. Okay, so this allows you to have an illusion of infinite memory. Okay, most of the time on your machine, if you look at the number of processes you have running, they will not all fit in RAM. Okay, only some small portions of them are going to fit. And the reason it all works out is your 90-10 rule, which is 90% of the time the process is touching only a small number of pages, the 10% of its pages. So you can get away by keeping the working set in memory and not keeping the rest in RAM. Keep the rest on disk, and the performance is still acceptable. Okay. So that's an important advance in memory management that's used today, even today, by all operating systems. Okay, and whenever you have on-demand paging and you have a page fault, a new page comes in, you have to decide which page goes out. Okay, that's your page replacement algorithm that decides whenever you have a page fault, which page you're going to evict. Okay, we looked at several, okay, starting with FIFO. Then we looked at one called opt or min, which looks at the page, which evicts the page that's farthest in the future. Okay. Optimal scheme, not practical, requires knowledge of the future. So basically, an approximation of min is LRU, where you look at the past and throw the page out that was least recently used. Okay. So that's the one that is used by most operating systems. But again, we said implementation of LRU is a problematic process because it requires additional data structures to decide which is the least recently used page. And managing pages in sorted order or keeping them as linked list just increases the memory accesses needed to do that bookkeeping. So you typically don't implement pure LRU, you use coarse grain approximations of LRU, of which we saw two, second chance and enhanced second chance, where rather than keeping a timestamp that tells you which is the least recently used page, you use a 1-bit timestamp, okay, or at most 2 bits, where you basically just use a bit to say is this recently accessed or not, rather than a real timestamp. And that bit you can put in the TLB, which you can efficiently update. Yeah, so implementation of LRU is sort of done in a very coarse, approximate way for efficiency reasons. Okay, so that was basically the material on memory management, and that's basic. So all the subsequent one is new material. Okay, so that goes beyond exam 2. So which was basically the material on I/O and file systems. Okay. As part of I/O systems, we essentially looked at the problem of how to write device drivers. Okay, so I/O devices are hardware devices. The piece of the kernel that talks to them are device drivers. So we looked at simple mechanisms to write device drivers. We looked at writing device drivers using polling. So we said every I/O device essentially can be thought of as a port which has 4 registers. Two I/O registers, one to write data out, one to read, a command register, and a status register. So the way you write a device driver, a trivial one, is you write the command that you want to perform to the command register. Okay? And then you basically, if you're reading data, then you wait for the device to have executed the command and you read from the read register. If you're writing, you basically write to the output register and then write out a command which says write, and then you let the device go off and do its own thing. So the simplest device drivers write to IO devices 1 byte at a time. For many devices that's okay, but for most devices that's far too slow. If you want to write a chunk of data and you have to write 1 byte at a time, that's going to be very slow. Yeah, so we looked at 2 or 3 different techniques to speed up IO devices. The most important one was direct memory access, where we said rather than writing one device 1 byte at a time, you basically give a chunk of memory to the device and give it direct memory access and go read this chunk and write it out, or read out some chunk and put it into this buffer. Okay. This allows you to speed things up because the CPU is no longer in the path. The CPU just gives one command and then the microcontroller on your device. Okay, the device will have a tiny CPU called a microcontroller. The controller will actually go off and execute that IO command. Okay, so what is a DMA? How is it performed? All of this is something you should understand and know, okay, for the exam. Okay, then basically we said to go into this a little more detail, we said let's take an example device, namely the disk. It's one of the more important devices you have on your machine. And we said how should the OS manage this device? Okay? And that's basically all the material on disks and file systems. So we said disks, at least the traditional magnetic disks, are slow. They have this rotating platters, and to read or write, you have to move a disk head to the right location before data can be read or write. So that incurs seek time, rotational latency. And we looked at mechanisms to reduce those overhead. That's wasted overhead that you will have to reduce. And the way you do that is by performing disk scheduling. Yeah, so we looked at several disk scheduling algorithms, starting with FIFO, SSTF. Even remember what that is? Shortest seek time first. Okay, we saw a generalization of that called shortest access time first, which we said is basically implements a traveling salesman type algorithm. But the most simplest and the most commonly used ones are what referred to as scan and C-scan. They essentially do elevator scheduling. Right? The disk head just sweeps from the innermost track to the outermost track, and whenever there is a IO request, it stops at a track, services the request, and continues sweeping. Just as an elevator, it starts on the lowest floor and it keeps going up. Whenever you need to either let somebody in or out, it stops at a floor. Let the people go in or come back up, and then it continues. So elevators go up and down. The disk head similarly goes from the innermost track to the outermost track and back up. Okay? So scan does that. C-scan basically is a variant where you service requests only in one direction. As you go, let's say, from the innermost to the outermost. In the reverse scan, you just go all the way back to the beginning, but you don't stop. If there are outstanding requests, you only service them as you go outwards. Okay, that's basically what C-scan does. So you need to understand what the algorithms are, given a sequence of requests, analyze how much disk seek overheads are incurred. We did several examples in the class on this topic. Okay, so file systems is something you spent a few lectures on. So I just defined what is a file. It's a named collection of data. Okay, files have names that you assign to them. Internally, the file names are mapped into numbers that the file. So every file has a unique ID, which is an integer that the OS assigns to it. And directories are simply tables that take a file name and map it to a file ID. And internally, you have to locate the file ID with metadata. Okay. So the important part here was what kinds of metadata structures are you going to keep around so that you can access data in the file efficiently. Okay. File accesses could be sequential or random. And we said we need to be able to support both of those types of access. So we looked at several file structures. If you remember, we said you can keep the file contiguous. In that case, the file cannot grow or shrink very efficiently. You may have fragmentation, but accesses are straightforward. Because once you get to a file, then all the data of the file is stored contiguously. Okay? Simple scheme. Cannot use it on traditional disks, but you can still use it in certain contexts where it's useful. Anyone remember where contiguous file allocation is useful? No.
single write memory devices?
Single write memory devices, which are essentially CD-ROMs, DVD-ROMs. So since you burn a CD or DVD once, you know all the files that are going to go on it. So you just use a contiguous file layout. You just burn it and you're done. After this, you're never going to modify a file. So there's no fragmentation or anything like that that you have to worry about. So contiguous allocation still used for file systems that are on write once devices, of which DVDs and CDs are a good example. Okay. In most other cases, you have to allow for files being deleted, files growing and shrinking. So you want efficient access even when the file system data on your disk keeps changing. And we looked at 2 or 3 different data structures there. One was a linked list organization for files, which is what FAT file systems use. We said that organization is efficient for sequential access, not very good for random access, because if you want to access the ith block, you have to start at the beginning of the linked list and keep scanning blocks until you get the ith entry. Okay, so it's not good if you have random access, which you will have in many cases. So to deal with that, we talked about index structures. We said you can use something called an inode, which is going to be an array of block pointers. So now if you want to access the ith block, you just look at the ith entry of the index. That tells you what is the disk address, and you just go and access that block. Okay. And very specifically in the context of index organization, we looked at a multi-level index, which is what Unix-like file systems use, where you have single direct block pointers, 1 level of indirection, 2 and 3 levels of indirection, where you optimize for the common case where files are small. But as files grow, you have multiple levels of index structures to traverse before you get to the block. So go back and review that material on index structures and understand how multi-level indexes work and so on. So those were the 3 structures that we talked about as to how files are laid out on disk. And most of those, other than contiguous allocation, most of those don't require data to be stored contiguously. Just as in paging, the disk has blocks or sectors, and you can allocate any block to any file. Files don't have to be stored contiguously. Okay, so keep that in mind. We looked at several other aspects of file systems, which is the API that the file system exposes through system calls, how a read call works, how a write call works, and so on. Something that you are actually looking at in Lab 3. So hopefully you are somewhat familiar with what those are, how they access files, and so on. Okay. So what you did in Lab 3 is a simple toy example of how a real file system works. Okay. We have a very simple lab where you have a fixed number of files. Each file has a very small number of blocks, and you are using an inode. You are using a single level index structure there. Okay. But in reality, you will have multi-level index structures to accommodate very large files. Okay, so I already mentioned direct memory access and polling here. The last thing we talked about in I/O systems and also file systems is this notion of caching and buffering. Okay, we said I/O devices are very slow. CPU is very fast, so there's a speed mismatch. Typically, if the CPU needs to do I/O, it has to wait for a slow I/O device to execute its request. So the way you usually speed this up is basically you put in a cache between your CPU and your I/O device. Cache is essentially could be in memory, and the cache holds recently accessed data from that I/O device. So whenever you want to perform an I/O request, you will first look in the cache to see if the data you are trying to read, let's say, is already there. If so, you just take it from the cache. You don't have to perform a slow I/O operation. Okay, so caches and buffers that are used for I/O devices are a big performance optimization that allow you to speed up I/O. Okay. The context of disks, we also talked about other optimizations like read ahead. We said if your file is being accessed sequentially, even before the application issues the next read request, you could have asynchronously read some additional data, brought it into the cache, so that by the time a request comes, it's already cached. So the performance is going to be significantly better. Okay? A lot of work that goes into the operating system to improve the performance of slow I/O devices. It's basically a problem that you have to deal with because of the speed mismatch between a fast I/O, fast CPU, and a slow I/O device. Okay. Last part of the course, distributed systems. Okay, so we started with the definition of what is a distributed system and how it differs from a parallel system. Okay, broadly speaking, a distributed system is a collection of CPUs that can communicate over a network. A good example is a set of machines that are working on a LAN. Applications run on these machines. They communicate with one another to achieve some higher level goal. The simplest example of distributed applications are client-server applications, where there's a client component of the application and a server component. And I gave the example of a web, where your web browser, web server, email, where your mail client and a mail server. Yeah, so client-server applications are commonly used to design distributed systems and distributed applications. Okay, we spent some time discussing the difference between distributed and parallel systems. A parallel system is a single machine where you have multiple CPUs. The communication medium is your system bus. A distributed system, your CPUs are independent machines. Okay, so that's something to keep in mind. We talked about many advantages of distributed systems. So you can share resources. Okay, since you have a network, one machine can access resources on another machine. That's a remote printer, remote disk. You have the ability to go access it over a network. You can basically use the CPUs on multiple machines to speed up your application. Okay, if you have n machines participating in your application or being used by the application, if you write your application well, you can have n times speed up because you have n CPUs and the CPU and the processing power of this n CPUs. So those are some of the advantages. There are some others, but those are the key ones. Disadvantages: your application becomes more complex because now you are not talking about writing code in one process. Your application is multiple processes running on multiple machines. They have to communicate with one another. Code is more complex. Okay. You have opened up your application to security problems, okay, because now some malicious parties can also access it over a network and so on. Okay. So there are some disadvantages, but nevertheless, most applications that you see that do something complicated tend to be distributed. Okay. So we spent a good lecture talking about networking, which was sort of the basic thing that you need to understand before you do something in the distributed systems or write distributed applications. Here we define different kinds of network. Local area network is a network that spans, let's say, a single building. Examples of it are Ethernet, Wi-Fi, and so on. Wide area networks are networks that span larger distances, whether it's a country, continents, and so on. Simplest example of WAN is the internet, which is a global wide area network. Okay. We talked a little bit about what is a packet. Okay, it's a unit of data that's been sent out by an application that traverses the network and reaches the destination. Okay. We talked about protocol stack. Okay, what is a network protocol stack? We looked at the layers of a protocol stack, okay, starting from the physical layer all the way to the application layer. And TCP/IP, I said, was an example of a typical protocol stack that's widely used. Yeah. IP is the network layer, which is responsible for hop by hop communication. TCP is basically the transport layer, which is responsible for end-to-end communication. If packets get lost, TCP will retransmit it. If you're sending at too fast a rate, TCP will slow down the transmission and so on. Okay. Now this is also material you cover in 453 clearly, but we add a very quick overview of this material just so that we understand how you write distributed applications. Okay. So then we talked about programming models for distributed applications, and we discussed RPCs and RMIs, if you remember. So RPC is remote procedure calls. RMI stands for remote method invocation. Okay. So at a very high level, this is how you write distributed applications without having to deal with low-level details of communication or networking aspect. Okay. Very simply, in RPCs or RMIs, one process can call a method that is implemented in a second process. Okay. When you write centralized code and you call a method, the code for that method is in that process itself. And that's how you write your application. You have different methods call one another. All of the code is in one address space. In RMIs, Basically, the code for a method is in a different process, maybe on a different machine, but you can invoke that method, have the method execute, and send back a response. Okay. RPCs and RMI systems make it easy for you to write such code. You simply call a method as if it's a local method, and the RPC or RMI subsystem will take care of all of the details, which is constructing a message saying this method has been called by this process, sending that message to the server. Server receives the method or the message, invokes the method, executes it, sends back the response. Okay. All of that extra code you, the programmer, don't need to write. That generated for you or handled by for you by the runtime system. We saw one example of a client server application using Java RMI. Okay, so go back and look at that code just so that you get a feel for how to write RMI code. Okay, we didn't have any lab exercises on this, so we skipped the lab part, but it's still good if you understand how RMIs work. How do you write Java code that allows you to call a method, a Java method that resides in a second process or somewhere on the network. Okay. Now, in the context of distributed systems, I also talked a little bit about at an abstract level, how do you write these distributed applications at a high level? Okay, so you can either do what is called data migration or computation migration. In data migration, the program actually moves over a network to where the data resides. In data migration, the data goes to where the program is. Okay. So I gave some very high level examples so you understand what this means. So when you do a web search query, okay, you type, let's say, some keywords in the search engine, that's an example of computation migration where the keywords form a search query. That's a tiny program that goes to wherever the index is stored by the search engine. So that's an example of code going to where the data resides. Yeah, there are examples we talked about of data migration where the program runs where it is, but the data is fetched over a network. Distributed file systems do this. You can write a code, it runs on a machine, but then the file resides remotely. The file is fetched and then you access it locally. And that's an example of data migration. And we talked about when each of this would be useful. Okay, if your network is fast, bringing data and making I/O local is always better if the data is small. If you have lots of data, it's better to send the code to where the data is. Okay, you will never have a search engine where you type a search query, you fetch the index and execute it locally. That doesn't work because the data is too large. I didn't say a whole lot about job migration other than to say that this is a way by which you can take a process that runs on your machine and the process can actually move to another machine. Okay, this is not something that you typically see in most operating systems where you are running application and then you just move it to another machine and the application continues to function. But there are systems that allow you to do that where the job hops from one machine to another until it finishes execution. So if one machine gets loaded, the job actually goes to another machine and so on. Okay, so but these systems are not in wide use, but they do exist out there. That's the third way of writing distributed application. You just start up an application, it runs on different machines over the course of its execution. Okay, so last up was distributed file systems. Okay, so we talked about what they do. It basically takes a local file systems, makes the files on that file system accessible to a second machine over a network, okay, or any number of machines over a network. Okay, we looked at some design issues. One is how do you use file names in a distributed file system? Should the file name include the name of the server or not? If the file name includes the name of the server, it's not location transparent. The file name does not have the server name in it, then it is location transparent. I give examples where you say if you have a file name of the following form. Okay, so this file name doesn't actually tell you whether the file is local or remote. Okay, in this case, if that's a home directory and the home directory resides on the server, the file is remote, but the name of the server is not there in the file name anymore. So this is an example of location transparent names. Okay, an example of what is not location transparent are web URLs. This is an example I gave, where you have the name of the server and you have the path name of the server, or a file name on the server. A name of this sort has the name server name embedded in it and a file name embedded in it. This is not location transparent when the file name includes the name of the server. Yet there are different file systems where you may have to do one or the other. And whether you have absolute names or location transparent names. And we saw examples of file systems like Windows NT file system uses this type of naming scheme where you have the server name followed by a path name, and NFS or Unix like file systems use this other scheme where you don't have to do that. Okay, so we talked about naming, we talked about performance optimization such as caching. Okay, so we said that two high-level ways to write a distributed file system. One is you take every read and write request, send it to the server. Server processes the request, sends back results. So files always reside on the server. All requests are sent to the server. And that's one method. The other method is a caching-oriented method where when you open a file, you fetch a copy of the file from the server. Now it's local and all reads and writes are then performed locally. And if you modify the file, you keep sending the changes over to the master copy of the server. Okay, these are two ways to write a distributed file system. Okay, use either forward all I/O requests to the server for processing, or fetch a copy of the file and use that local copy to service I/O requests. Okay. There are advantages and disadvantages of both approaches. Okay, we talked about what happens if the file server goes down. Okay, if you have data that hasn't been saved, or not file server, rather the local client goes down. If you have modifications there that haven't been sent to the server, they will be lost. Or if two clients open the same file, if there are two copies and they're making independent changes, then you will basically not be able to see the latest copy. Okay, so cache consistency is something we talked about in this context, saying how do you make sure that the data that you see is always consistent. Yeah, this is a bigger problem in distributed file system than it's in local file system. So in local file system, there's only one copy of the file. In a distributed file system, the same file may have multiple copies or copies in caches. So you have to deal with that issue of not giving stale data to the application. Okay. And then we had this short lecture on protection and security. Okay, so this is basically the problem of ensuring that only the right users or the right processes can access resources. Okay, so the simplest way to think about this is if you have a file, how do you ensure that the file is only accessible to certain users or certain processes but not to others? Okay? That's basically the problem of protection. We said the way we implement protection in operating systems is through a notion of access rights. For every object, you have a set of access rights which say who can perform what operation. Okay? User 1 can read and write to the file. User 2 can only read that file but not modify it. User 3 can neither read or write this file. So you specify these access rights, okay? And then those access rights are actually stored by the operating system as an access matrix. Okay? For every object and every user, okay, you basically say what can that user do with that object? What rights do they have on that object? Okay? So that access matrix allows the operating system to decide what operations are valid and not. So before any read or write on an object is allowed, you always check the access matrix. Does this user or a process that belongs to that user, is that able to perform this operation? Okay, is it present? If the operation is allowed by the access matrix, you let it through. Otherwise, you deny it. Okay, this is how you actually check for file accesses and so on. So we said there are two ways to actually implement your access matrix. One is the access control list, okay, which is a column-based organization. With every file, you store a list which says what operations can each user perform on that file. That's called an access control list. You can also have a different organization where you have a row-based organization called capabilities. So rather than storing access rights with objects, you store access rights with users. Right? Users are given a list saying this is what you can or cannot do in the system. So before performing an operation, the user then shows the OS a certificate that says, here is an operation I want to do. I want to read this file. Here's a certificate that proves that I have authority to or access rights on this file. Okay, and now OS will check that capability and decide whether to let it through or not. So either you store access rights with users or you store access rights with objects. And these are the two ways by which protection is actually implemented. Okay, so that is basically what I have for a quick overview. I spent about half an hour. I'm going to pause, take some questions here, and then I have some final things to say, and then wrap up for the day. We'll have course evaluations also. So let me pause here and have you ask questions. I think the attendance was somewhat thin in the last few lectures, so I don't know how many of you attended how many of these classes, but all of what I said since IO systems is all going to be on the test. So I'm going to have you ask questions if you have any. We also had two guest lectures, one on Linux and one on cloud. I didn't cover that as part of this. So those are also something you should keep in mind. Yes?
The Linux might be on the final, but not the cloud.
Yeah, everything we have done is fair
Okay.
game for the
Both of
test.
them might be.
You don't need to go and read up a lot of material, just reviewing the slides would be good. Any other questions? So that's a fair bit of material to read, and that's an entire book. Okay, you will not be well served by starting from the first chapter and reading the whole book. And what I would recommend is what I had said previously, you look at the course slides, and only material that we have actually covered in the slides is something you should worry about for the test. And something that is not, there is material in the book that we did not cover in the lecture, don't have to worry about that. Okay, so the right way to go about this is there are lecture slides and lecture notes. Start with those. Okay, make sure you understand that material first, and then review the book so you can get some additional details on that material. That's the only smart way of taking an entire book and making sure you are up to speed for the final. Okay, yes, question.
Are these a good indication of your vision?
Yes, the course wrap up is basically what we covered. But as I said, if you look at the lecture slides, whatever I said here is reflected well on the slides. So the slides are basically the best way to start reviewing material. Yeah, the videos are also there if you need to go back and listen to lectures. We have been posting the recordings of classes as well. Any questions here before I wrap up? Okay, so as I have said before, general understanding, typically there are two types of questions. Questions that say define some concept to know whether you understood it or not, and questions that ask you to use that concept to do something. Like we give you a scheduling algorithm and a set of requests and say show us how it is scheduled and what kind of wait times you will see. So the same kind of questions you should expect on the final. You don't have to write real Java code. At best, pseudo code, as you have done previously. There are not going to be very specific questions about any particular operating system other than the one Linux class that we studied, and even that material was so high level you don't have to worry too much about it. But we don't ask very specific questions about platforms and so on. Mostly test questions deal with concepts and applying those concepts in a particular way. Okay. So very last thing I want to say is there are 4 or 5 takeaway messages from this course in operating system. When I started the course, I said this is a course on OS, but it's also a course on understanding how to design large software systems. Okay, because there is no such class that you actually have in the curriculum that says how do you write a very large piece of software. The OS is a proxy for a piece of software that's pretty big. Okay, most commercial operating systems are millions or tens of millions of lines of code. Okay, so what you have gone through this course is an understanding of what design decisions to make, how do you make the right trade-offs and so on. And these are some higher level messages that come out of how do you design large software system. Okay, first one is simplicity. Okay, so you want to strive when you have very large pieces of software to keep things as simple as possible. Okay, because you're dealing with very large pieces of code, and if you make some part complicated, it can have a ripple effect on many other pieces. Okay? So simplicity is easier said than done. Okay, you always think that adding more functionality may be good because of it has some benefit in certain corner cases, but that functionality should be added after a great deal of thought, because more functionality you add, the more complicated your code gets, the slower it runs, and then harder it is to maintain. When you're trying to maintain a software base of, let's say, million lines, 10 million lines of code, simplicity is going to be a very big advantage. The more complex your code is, the more bugs there will be, the harder it is to get it out in a usable form. And you see this often. A large update comes out to some piece of software, always riddled with bugs, never perfect. Lots of things start breaking, and then it has to be fixed after the fact. And then, so simplicity is sort of the first and the biggest takeaway message is when you have large pieces of software. Okay. Performance is another one. I'm going to actually show some details of. I took this from another professor. So, designing a system for good performance, another important takeaway message. Over and over again in this course, we talked about, okay, if you wanted to implement this concept, how would you do it? Is there a problem when you do it in a certain way with respect to performance? Because this is an important issue. Your users will not use your software if it is too slow. Yeah, or if the performance causes some problem that causes the software to break. Okay. So you can deal with performance in two ways. One is you try to make every line of code as fast as possible. Okay, that's not typically a good way to write software. The reason is most of the problems, the 90-10 rule also holds in performance. Most of the issues, performance issues in your code lie in 10% of your code somewhere. And that's really where the bottlenecks lie. The rest of the code, even though it may not be the most efficient, is not the cause of the slow performance of your system. Okay, so focusing your effort on making that 10% fast is where you are going to get the biggest gains. Okay? So the real crux of the issue is to understand what is the slowest part of your code. Rather than saying, I'm going to make everything fast, find out where the problems are, where is the performance problem. Only focus on that, and then you'll get the biggest bang for the buck. You only focused on a small part of your system, you made that fast, and everything sped up. Okay? Now, that's easier said than done because it requires you to use tools to find out where the code is slow. Okay, just looking at some piece of code, you cannot tell typically is it going to have good performance or bad performance. So you use profilers, you use performance tests, you can use models to figure out how your different parts of your code are actually going to perform. And then you tune the part where you see the biggest problem. Okay, that's how you write large software systems. You don't go and say, I'm going to make every part of the code as fast as possible. Okay? That's something to keep in mind as well. So it's a skill to learn. It's not something that is immediately evident when you write code. Okay? Third thing is programming, which is what you all do, is something that you need to learn to do well. It's something that you will be using as part of your job and so on. And it's as much of an art as a science. Okay? The right pieces of code that you write are something that basically reflects how you design it, how you think about it, how you write it. Is it clunky? Is it elegant? Is it simple? All of this is basically something that's reflected from whatever code you write. Okay, so there are many rules to keep in mind. Okay, I already mentioned simplicity. Okay, it's something very important to not add complexity for no good reason. Okay. Something that goes with that rule is don't overgeneralize. Your code should not be too narrow. It should be able to handle some general cases. But if you make it too general, it becomes not very useful at all. Okay, because very general code is going to be a lot more complex. So understanding what is the common case and optimizing for it is an important takeaway message. As an example, I'm going to refer you to our discussion on file systems and specifically the index structures. Okay, we did not design the index structure for the worst case, which is the largest file in the file system. We said let's make it a multi-level index. The common case is small files. Let's optimize it for the common case. Okay, that doesn't mean that we will not be able to handle large files. Okay, we will by creating additional levels of index structures. Okay, that's a good example where we did not think of only the worst case and write the code for that, and then basically have the common case have very bad performance or and so on. So that's a good takeaway message for programming. Another rule is if it gets too complicated, you always try to make simple fixes. Yeah, sometimes it's not a bad idea to throw it all out and restart. Okay, band-aids can only do so much when major surgery is needed on your code. Okay, but making that call saying, do I throw away all the effort I spent and start over? Not an easy decision. Okay? Most of the time, you always fall in the trap of let me just fix it and get it to work. But then the code lives for a long time and the problems never go away. Okay? That's sort of an important aspect to keep in mind. Get modularizing your code, testing individual modules. Okay, something you learn hopefully in software engineering, but we have seen that even in operating systems. We said the most common architecture for kernel is the modular architecture. There's a reason for that because you cannot understand every single piece to make small changes. So you write modules, you basically put all of what is needed to be done in a single module. Modules talk to one another with well-defined interfaces and so on. Okay, and then you can test each individual module as well, make sure that module works well. Okay. So modularity of your code is important. Making sure you have consistent style within your application or code also important. You may not be the only one modifying this code down the line. If you have really different styles used in different places, that causes confusion. Okay, so some of these are more rules that you adopt in writing code. Okay, don't make quick fixes because they will only hurt you. Okay, that's what I meant by putting band-aid. Because then later on, those quick fixes will come back and haunt you because you have to then make major design changes. So doing it right is important. Documenting is even more important because when somebody else makes modifications to your code, if they don't understand it, they will make incorrect modification. The most realistic software projects will have tens, hundreds of people working on it. Okay, just as you expect somebody else's code to be understandable, your code should also be understandable to someone else. Okay, so this is why we have been emphasizing documentation and so on in the labs, okay, because this only comes through practice. Okay, the easy way is let me not write any code. Code is self-documenting. Okay, code is never self-documenting. If somebody else reads it, they don't understand what you had in mind. Okay, so something that you need to keep in mind. Okay. Trying to put the documentation near the code and having design docs important, ensuring quality of the code also important. Okay, writing fast code is good, but writing good code is even better. Okay, all of these things only come with practice and not something that you will just acquire just because I said so or somebody else said so. Okay. So last two things are information is property. So information is intellectual property. You need to guard it well. Make sure that you deal with it in the appropriate way. Okay. So respecting that is also important. Okay. Last take-home message is that you need to stay broad. Okay. The very first lecture had a history lesson of operating systems, and I also explained how every few years the technology changes, things evolve. So you really need to, if you want to keep up with things, okay, so if you have a 30-year career, anything that you know now, in 5 years from now will be obsolete because technology is changing very quickly. Okay, so the only way to keep up and not be very narrow is to stay broad. Okay, keep up with what's going on. If you specialize in something very narrow, you may be outdated. Okay, so in no time, and then technology moves on, new skills are needed, and you don't have those skills. So something that you will need to keep in mind. Okay, in this field, learning is going to be a lifelong process. Okay, you will not be writing code in Java 30 years from now, so some new languages might come up, not just 30 years, even 10 years from now. Some of what you learn now is not going to be relevant. Okay, so how to keep up is going to be something you will have to keep in mind. Okay, so the right way to do this is have the breadth so you can assimilate new ideas, new technologies, new languages, and keep up. That's the only way you are going to have a good career when you get out of here. Okay? So that's basically where I'm going to leave this. Okay? So I just wanted all of these messages to sort of come out of all of the discussion we've had. I'm going to stop here for today and also for the course. So what we have, the last point that we have to deal with here is the course evaluation. Okay, so I need a volunteer to administer it. Somebody wants to deal with this. Okay, so you know how the course evaluation works. So just I would appreciate your feedback on what you thought was good or not good. Okay, there are comments on the back. Take some time. Provide me that feedback so I can use it to improve the course in the future. Okay, other than that, as I said at the very beginning, we're done with the lectures. Okay, you still have labs and homeworks and all of that due, but I am available next week after you're done with your assignments. If you want to stop by and ask questions for the final, I will continue to have office hours, okay, all the way through the final, which is on Friday. So let me stop here. So